So we'll now move on to the second part of our lecture, which is the sequential logic elements themselves. So let's start with a couple of naming conventions. In our course, we'll relate to registers in the following ways. A latch is a level-sensitive register. So as you can see here, if we have a positive latch, when the clock is low, this is representing the clock, the latch will be opaque. In other words, it won't allow the transfer of the data from the input to the output. And when the latch is high, when the clock is high, the latch will be transparent, and then the data will be mirrored onto the output. A flip-flop, on the other hand, is what we call edge-triggered. In other words, it only samples the data on the rising edge or the falling edge, but usually we're talking about positive flip-flops, positive edge flip-flops, and it only has a singular point where the clock rises, where we'll actually sample the input to the output. During the entire clock cycle, other than the singular point of the clock edge, our flip-flop is locked, and it will block anything that happens on the input from appearing at the output. There are different naming conventions that you can be found in different places. For instance, many books call any bistable element a flip-flop, such as an SR latch, but this leads to a lot of confusion. We'll use the convention above, and in industry, we really talk about a flip-flop as an edge triggered register versus a latch as a level-sensitive type of a register. Often we'll also say register, meaning a flip-flop, even though it could relate to both. So when we discuss latches versus registers, let's see how it kind of works. So during the high clock phase, a latch is transparent. Again, this is a positive latch, latching the input on the falling edge. So this is very kind of odd. When we have a positive latch or a positive edge latch, it actually latches the input on the falling edge or samples it on the falling edge. So we have here the clock, okay, and we see that the clock goes through this period that it keeps going up and down, and we have some sort of an input that we just drew the input, how it's going to change. It doesn't really matter what the input is, but we will see what happens. So when we take a latch over here, what we do is we can mark the area where the latch is transparent, and the latch is transparent where we have these green areas. So what essentially is going to happen is that when we have this area where the latch is transparent, we're going to take the input and copy it to the output. So we're going to get a 1 over here in this area. In this area, we're going to really copy that from 0. It's going to go up to 1 and then stay at 1. And in the next area, from 1, it's going to go down to 0, where the latch is transparent. At the areas where our latch is opaque, what we're going to actually do is we're just going to keep the state that we were at prior to the falling edge, and we're going to keep it, okay? And we're going to have the transition once we open the latch at the positive edge. So we essentially sampled the latch here at the falling edge of the clock over here. Okay, we locked in what was there. So again, here's the falling edge of the clock. We lock in what is here, and we copy that along. Okay, and as we can see, this is the waveform that we expected to get. So that's how we see how a latch works. And again, what we have is during its transparent phase, which in this case is a positive latch. Usually you see that by the clock input doesn't have a circle on it. If it has a circle, it's a negative edge latch, a negative level latch. Okay, so we just copy the input to the output, and at the opaque phase, we just sample what was before and keep it that way until the latch reopens. Okay, a flip-flop, on the other hand, only samples the input on the rising edge. So for a flip-flop, we take the clock edge, and you see that we mark the clock edge with these little arrows. That's showing that we're using a positive edge approach. We could have marked it on the negative edge and use a negative flip-flop by putting a little circle here down at the bottom. But again, what we're going to be using by standard is a positive edge flip-flop, which samples the data at the positive edge. So all we have to do really is look at what the data value is where we have these arrows. So we see that the data value here is a 1. So the flip-flop is going to turn into a 1 over here, and it's going to keep that value until the next positive edge. Now at the positive edge, we're going to sample, and we see that there's a 0 here. So here the output is going to transition down to a 0, and it's going to stay at a 0 until the next positive edge. Here again, we sample what we have in the data. The data is a 1, so it's going to rise and keep that level until the end. and you can see that that's what I pre-prepared. That's how we can figure out what a flip-flop output is going to look like. So again, what a flip-flop does is it samples the data at the positive edge of the clock, and what a latch does is it transfers the data during its transparent phases. So there are three main options for sequential timing. The first one is using flip-flops, and this is what's commonly done in 99% of the ASICs that we're going to purchase or design. We're going to use a positive edge triggered type of a timing approach. So we have these flip-flops. Usually we'll draw the clock input with a little triangle to show that it's an edge triggered element. And again, we have some sort of combinational logic, some sort of Boolean algebra function that is in some sort of logic cloud between the flip-flops. There are going to be several flip-flops or mini flip-flops that are going to be the launching flip-flops, the start points, and there are going to be a whole set of other flip-flops at the end point. There are different paths between this set of flip-flops at the beginning, this set of flip-flops at the end. There can also be feedback loops because a flip-flop at the end, a flip-flop can belong to both sets, and this is going to be how we're going to clock them. We're going to sample everything at the first flip-flop and sample it again at the following flip-flop. And since the clock period is set according to the worst case delay, the longest path that goes through these flip-flops, we make sure there are no races between the data. Everything is synchronized by the clock. Another option is to use transparent latches, and we'll see in a few moments that actually a latch is the basic element that makes a flip-flop. We kind of chain two latches together to create a flip-flop, and so what we can actually do is we can break this operation between clock edges into 2 points where we have a positive latch, another positive latch, and a negative latch between them, and use a kind of a half cycle phase and get some additional things such as time borrowing between the two latches. This is a more complex type of a design idea. I'm not going to be going over it in this course, but it is something that is done once in a while in industry when a truly high performance is necessary. Another option is a pulse latch. Well, we can take a latch and just give it a clock pulse, a small clock pulse, and we'll see how to do that with a clock chopper later on in the day. And by adding this small pulse, we actually have the latch be transparent only for a short amount of time, and therefore it kind of emulates a flip-flop. It's almost a singular, like, small point where the latch is transparent and the data can go through, and then we can use a latch, which is much more cheap. It's almost half the size of a flip-flop to do the same type of operation as before. So those are three types of options that can be found for sequential timing, but really most of the time, unless something very aggressive is necessary, we're just going to be using the first type, which is using flip-flops. So how do we actually make these latches? Well, there are two, I guess, basically types of latches, a static and a dynamic latch. A static latch, and this is going to be the type that is most commonly found, just like we use static CMOS type of logic. We like static things that replenish their data at the output, even if there are all kinds of noise and leakages. So static latches are very commonly used. And a schematic, a high-level schematic of a static latch is just a multiplexer. Okay, we have a multiplexer. These are D flip-flops. Okay, so the D input, the input of the flip-flop comes into 1, usually the 1 selection input, and there is feedback from the output, which is usually called Q, into the 0 selection input. And what happens there is that when we have the clock over here, if the clock is at 1, we take the D input and we propagate it to the output. When we have a 0 over here, we take the output and keep it latched inside the element. So what we're doing is in the 0 phase, we're opaque. Anything that happens on the D stays at the D. It doesn't go through the latch because this path is selected. When we go into the 1 stage, then everything from D comes into Q. That makes the transparent stage of the latch. A dynamic latch, on the other hand, can be just a simple type of a sample and hold circuit, at least conceptually. So we can take some sort of switch, okay, it could be a transistor or something like that, and connect its gate or its control to the clock. And when the clock goes to 1, we close the switch. that connects the D to the Q, and obviously anything that happens at D propagates to Q and is mirrored at Q. Once we open the switch, okay, so the clock equals 0, then we cause an open circuit over here, and whatever was stored on the capacitance stays there, and anything that happens on D doesn't affect the output. So this can also be called a sample and hold type of a circuit in analog design. And this conceptually is a really simple way to make a latch. The problem is that it's a dynamic circuit, so everything depends on this parasitic capacitance, and any type of noise or leakage will deteriorate the level, so it's only a temporary type of a storage. So, as with logic, this provides a trade-off between area, speed, and reliability, where obviously the area and speed of the dynamic latch will be better than the static latch, but its reliability will be much lower. Some basic implementations of the static and dynamic latches that we saw in the previous slide, you can see over here. So this is just a transmission gate based multiplexer. So we have some buffer at the input to just make it CMOS-like. So we see a high capacitance at the a high resistance with a capacitive input at the D input. Okay, we have a pass gate, which is on when clock equals 1 and off when clock equals 0. And this goes into a buffer that shows us a buffered output to the Q, and the buffered output goes through a feedback loop where we have a pair of cross-coupled inverters, which causes bistability. So if we put a 0 here, we're going to get a 1 over here, and the 1 is going to turn into a 0 over here, which is going to turn into a 1 over here, and the 1 and the 1 agree with each other, so we get this bistability, and we strongly hold this operation. So once clock goes down and this transmission gate closes and this transmission gate opens, we're going to have the same value on both sides of the transmission gate. There's no contention, and we hold this type of a state where we're going to have 0 at the output of the latch, which is what we sampled when the clock when the clock went down. Okay, as I said, these latches sample on the falling edge of the clock. Okay, so that's how we get a static latch. This is just, again, a multiplexer with the feedback loop from the 0 input back into the from the output back into the 0 input. The dynamic latch, we can show it again like this. So we have a transmission gate, which when clock equals 1, it's going to be open, and we're going to pass D into the output. We would buffer probably the output to make it a nice level over there. We'll probably use a CMOS transmission gate in order to get a full rail-to-rail swing. And we have some sort of parasitic capacitance that's going to hold our state once we close and turn off the transmission gate and keep ourselves latched. So that's a kind of a transistor level implementation that could be used for static and dynamic latches. Another category of that we should see about latches are ratioed versus non-ratioed latches. So again, what we can do is make the static latch a bit more simple by just using a feedback inverter. Okay, so we have the transmission gate over here with the buffer, which made our dynamic latch before. But if we actually come in, let's say we had a 0 over here that made a 1 over here, we add a small inverter in the feedback loop, so it gets a 1 at the input and a 0 at the output. Again, we latched a state that is going to be statically held very well. This is not going to deteriorate or replenish. This bistable circuit, which we'll see later on in the course, is the basic memory element that's commonly used in general in CMOS and in VLSI. Is going to hold this state very well. It's not dynamic, it's going to be static, and there's no problem. The problem that we have here is that when we want to change and overwrite this to a 1, we'll put a 1 in D, and then we have a contention between these two guys, and we have to make sure that whatever is driving the 1 over here can overcome the feedback of the NMOS in this inverter that's trying to pull down and hold this circuit at this node at 0. So this is ratioed logic. Again, we'll have the driver that's coming from over here fighting against the feedback that's coming from over here. We need this feedback to be very weak in order for the driver to overcome it at any rate. So it's usually more robust to make a non-ratioed latch, and the MUX-based latch that we saw before is non-ratioed. Once we go from the 1 state to the 0 state, we're actually closing one of the transmission gates and opening the other, and then there's no contention over here. Again, once we close the other one, we break the feedback, and if there was a 0 here and we override it by putting 0 here and a 1 over here, there's nothing that's contending it, nothing pulling it back down to 0, and so this will become a 1 over here and drive our output back to the state we wanted. Again, this will then be conveyed back over to here, wait as a 1 over here, and once we again change our clock phase, this cuts off, but we have no contention over here. These are both happy to be 1s and are stable at that state. So this is a non-ratio latch, and this is a typical type of thing that's used to improve our noise margins, improve our robustness of our circuit. So how do we make a flip-flop? And I mentioned it before. The conceptual way to create an edge-triggered flip-flop is to combine two opposite polarity latches. So here you can see I put a little circle over here, which means this is a negative latch. In other words, it's transparent during the low edge of the clock, and it samples on the rising edge of the clock. And here's a standard latch, which is a positive latch. So we have a negative edge latch followed by a positive edge latch, and let's see how that works. So we have the input over here, and we take our negative edge latch over here, and you see that the green area is where this latch is transparent, and the red area is where this latch is opaque. So again, what we're going to do basically is we're going to follow what the signals should cross here. So again, in the green area, we copy the input, so we're going to get something like this at the midpoint over here, right? Then over here at the green point over here, we're going to copy that again. So we get this. At the green point over here, we're just going to stay with a constant 1. And of course, what we're going to do is we're going to sample the values here and here and here and copy them until they connect to the next point. Okay. And so we see over here that that is our midpoint. So that goes into as the input to our positive latch, and here the green areas again are the transparent areas. So for the output, we're now going to copy the input, which is now just a constant, okay, and copy the input over here. Remember, at the falling edge over here, we're going to sample whatever we had at the falling edge and keep it straight, and then just make the transition once the latch is transparent again. Okay, again at the falling edge, we're going to sample what we had here, keep it straight, and enable and make the transition when it becomes transparent again. And again, we saw the output over here. So what do we see here essentially? We see that at the rising edge of our clock, which are these 3 points, what we do is we're going to sample our data, a 1 over here, a 0 over here, and a 1 over here. And what we got is we got a 1 from here until the next clock cycle. Okay, as we can see down here. Here we got a 0 from here until our next clock cycle, as we can see down here. And at this rising edge, we got a 1 until our next clock cycle. So you can see that we demonstrated how just this cascading of a negative and a positive latch turn into a flip-flop. So this is generally called a master-slave register, an edge-triggered register. So this is the master latch, and this is the slave latch. And here we can see a high-level schematic of how to make it. We take one of these muxes that the D is connected to the 0 selection input, and the output is fed back into the 1 selection unit, versus the positive latch where the D is connected to the 1 selection input, and the output is connected back into the 0 input, as we saw before. And this will behave as a flip-flop, and this is how flip-flops are generally made. So if we go down into a lower level schematic, we can see here that what we'll do here is we'll take the clock, we make a positive and negative and a flipped clock in order to control the transmission gates. We have these 4 transmission gates which help our muxes, and our muxes are well buffered in order to make them robust CMOS type gates. And we get our master type of a stage and our slave type of a stage, and that provides the flip-flop. Okay, how many transistors make up this flip-flop? So if we count it, there's something like 22 transistors. Actually, in real life, it comes in, it gets a bit bigger than that. We can get 30 or more transistors in one flip-flop. But maybe a more important question of how many transistors. And remember, when we're talking about 20, 30 transistors, that's much more than an inverter, which would be 2 transistors, or a NAND or NOR gate, which are going to be 4 transistors, right? So this is a big, big, big cell. It's going to be one of the dominant or biggest cells that we're going to use in general. But another important thing here is what's the clock load of this type of a thing. So you see that the clock input goes, and it has 2 transistors over here, right? That it has to drive. Then this guy has to drive this transistor, 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 right? So we have quite a lot of a clock load. We have 8 or 10, depending how you count it, nodes or gates of transistors that we are driving with the clock. And remember that the clock keeps on toggling. It's going up and down with a very high activity rate, maybe an activity rate of 1 if we don't use all kinds of clock gating techniques. And so this is going to be using a lot of energy, and it also it loads our clock, so we have to actually use bigger drivers, because we're going to have thousands and hundreds of thousands even of these flip-flops in our design, and they all need to be driven by some sort of a clock tree or something like that. Just a couple more points about the design of flip-flops. So usually when we have a state machine, we're going to want to reset it and bring it into its initial like idle state or something like that. We need to know what our reset vector is, what our reset value is. So we need to be able to reset these flip-flops, bring them into a state of 0 or 1 to get to a pre-known state when we start our design. Okay, so how do we reset our flip-flops? There are 2 categories of resettable. One is asynchronous and one is synchronous. An asynchronous flip-flop means that we cause it to go into its reset or state regardless of the clock edge. If we pull one of our nodes to either the set value or reset value, set means turning it into the state into 1, or reset turning it into 0, it's going to happen immediately without any regard to the clock. So you can see over here that we have our kind of a mux-based flip-flop. These NAND gates, they replace our internal inverters that provide the feedback, and so we connect to the new node that we added here. To these NAND gates, we connect the reset or set signal, okay, to bring it to a 0 or to a 1, and they cause, because it's a NAND type of a gate, when we stick a 0 in, we get a 1 at the output, so they cause to drive the initial or the inverted node to 0 or to 1 immediately when we do it, regardless of the state of the transmission gates, which are controlled by the clock. Okay, so that's how we can make an asynchronous set-reset flip-flop. Of course, if we only need a resettable flip-flop, that means that we can only reset it to the state 0, or we only need a settable flip-flop, which means we can only set it to the state 1, then we don't actually need both of these signals, and we can reduce a few transistors inside. Okay, the other option is a synchronous reset flip-flop. Okay, and here I'm only showing the reset option. You can have the same thing for a set option, and in this case we have a cheaper flip-flop because we only put the reset, we only change the input buffer to a NAND gate, and we change the input to the reset signal. This of course will only propagate through the flip-flop once we enable the transmission gates on the positive edge of the clock. So this is not asynchronous. It happens only on the clock edge. There are 2 large philosophies of how to design sequential circuits, with asynchronous reset or with synchronous reset, and these are the elements that support those 2 types of design approaches.